Greetings and welcome to the complete lecture for Chapter 4 of Chemistry 221 called Chemical Bonding in Molecular Geometry. And what this is all about is we're going to see kind of the patterns that chemists see when you want to talk about how a molecule is held together. And along the way, that we'll be able to explain several things, like why some compounds have higher boiling points and some compounds have lower boiling points. And also, if you just look at these different molecules, they all are quite different. So some of them have really wild geometric designs. The thing in the center middle there has a very geometric, kind of almost cubic design. And you can see there's a lot of different patterns that chemists see. And we'll be able to understand at the end of this chapter where these patterns all come from. So this is kind of a cool chapter and kind of talks about how molecules are put together. Let's check this chapter out. When it comes to the type of glue that holds atoms together, there's basically two different kinds called ionic and covalent bonding, and we'll look at both of those. And when we look at ionic and covalent bonding, we want to know some things like how are the molecules held together? Like what is the glue that kind of keeps the atoms stuck to each other? Why are the atoms at all these weird angles? Like you'd think they'd be just like AB, AB, AB linear, or maybe something like that. But in reality, you see a whole bunch of different varieties. Why aren't they all flat? All right, another good question. Can we predict the structure of new molecules? Like you make a new molecule with a biochemical marker in it, maybe you can make some predictions as to what it looks like. And also, of course, as a chemist, it would be cool to know how the structure is related to the chemical and physical properties, like the melting points and boiling points, what things will react with what, stuff like that. So those are the kind of questions we're going to go through as we talk about this section, and it's amazing how well chemists are able to answer these things, as we'll see. So there's two extreme forms of bonding, which is the kind of glue, if you will, that holds molecules together. And the first one, which is the strongest, is ionic bonding. And in an ionic bond, some atom gives up an electron to another atom. It's a metal giving up an electron to the nonmetal. So as you can see from that example right there, sodium metal has one extra electron on the outside, and it's happy more or less to give up its electron to chlorine. And chlorine has a spot for it there. And when that happens, you end up then with a positive sodium because it's lost an electron, and a negative chlorine because it has an extra electron. And that positive-negative attraction is actually quite strong. It's called an ionic bond. It's one of the strongest kinds of atomic bonds that are known. And sodium chloride, you can see in the upper right-hand corner there, has alternating sodium chloride ions. In that diagram, the purple atoms are sodiums and the chlorines are green. Anions are usually bigger than the atoms they come from, and cations, like sodium, are usually smaller than the atoms they come from. So the smaller atoms will be the sodiums, the purples, and the bigger ones will be the chlorines or chlorides, the greens. But there's another kind of bonding which is really important too, and it's called covalent bonding. In a covalent bond, the atoms don't actually donate electrons to each other. They actually share all of the electrons. So this is kind of the sharing bonding. Covalent bonding is certainly not as strong as ionic bonding, but it's very prevalent. It's mostly common amongst nonmetals with nonmetals, like nitrogen there on the right-hand side. Now you'd think that at first, like, oh, covalent bonds must be lame because they're not as strong as ionic bonds. But in all fairness, covalent bonds, being not as strong, are much more flexible. And when you're talking about life forms like you and me, you need flexible bonds. You need bonds that can attach and detach relatively easily. And a covalent bond does a really great job for that. So just because they're weaker doesn't mean that they're lame. All right, there actually are a lot of uses for covalent bonds, as we'll see in this chapter and beyond. Now, most bonds kind of have a mixture of both ionic and covalent. And so chemists will talk about them as mostly covalent or mostly ionic. And sometimes it's really hard to tell, like the metalloids on the periodic table kind of fall in between there usually. But we'll talk about all this as we go through. Now, to be fair, there are other types of bonding. We won't talk about them so much in our classes, but I want you to hear these names. Metallic bonding is used for pure metals. So if you have a pure aluminum metal sample, that's going to use use metallic bonding or sodium or mercury, etc., etc. Metavalent bonding is a brand new type of bonding scheme for metalloids that people have developed. And that's a very, very new within the last couple of years kind of a bonding scheme. So there are other kinds of bonding, but most of the time you can get by really well with just understanding ionic and covalent bonding and know if they're kind of halfway in between. It is important to know when you have a compound which is ionic, covalent, or metallic, and we'll develop our skills on this as we go through. But overall, an ionic bond is usually present between a metal and a nonmetal, or a cation and an anion, while a covalent molecule usually has nonmetals with nonmetals. So you won't see any metals in a covalent bond usually, although we'll come back to this in Chemistry 223. Metallic bonds would be just for pure metals. So if you had a sample of just copper or just nickel or just cobalt, something like that, then you would have a metallic bond.
A crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
Ionic bonds are very, very strong, and sometimes in the macroscopic world, the world of you and me that we see with remote controls and pencils and computers and stuff like that, sometimes the things we see actually are represented on the atomic level. This is potassium bromide, which has very strong ionic bonds. You can see every other potassium bromide. Again, the smaller ones are usually the cations, and the bigger ones are the anions, so the smaller green ones are potassiums, the bigger red ones are bromides. But anyway, you can actually see this in the crystal structure then of potassium bromide. So it's a very, very strong kind of bond. So if you hear electrostatic forces, people are talking about ionic bonds, things with a positive and a negative charge. And Coulomb's law, which is a law that's used to talk about positive and negative attraction, is what chemists can use to talk about the strengths of the bonds too, which is kind of cool. This equation up in the upper right-hand corner is Coulomb's law. And in physics, you might actually calculate the newtons, which is a type of force, between the positive part and the negative part. But in chemistry, at least at this level, what we're going to do is we're going to use the results of Newton's law, but we won't actually talk about Newton's law. So what I'd like to do is I'd like you to focus, first of all, on the top part of this equation, where there's n plus e times n minus e. So first of all, the positive and negative, that's the positive like metal cation, and the other part is the negative non-metal anion. And you can have more than one charge, like you can have a positive 2 or a positive 3. That's what the n means. It's the number of positive charges. And the n by the minus would be the number of negative charges. Like oxide is 2 minus, that would be n of 2, etc., etc. But anyway, what that's trying to say is that the number of positive and the number of negative charges will make your force go up. So if you have a positive 1, negative 1 interaction, which you see in the middle kind of part right there, it's very strong. It's like a single handshake. It's pretty strong. It'll keep the molecule together, definitely. But oh boy, if you have a positive 2, negative 2, like on the bottom one right there, that's even stronger. It's like a double handshake, which would be harder for a person to break up than a single handshake. So the more charges you have, the more the force is going to kick in, and your thing will be a lot stronger. So that's what the top part of Coulomb's law says. Positive 1, negative 1 is strong. Positive 2, negative 2 is much stronger. And if you happen to have a positive 3, negative 3, that would be stronger yet. It gets even more and more intense. But there's another part of Coulomb's law which is important, and that's the denominator, the bottom. It's the distance between ions. And you can see in the lithium fluoride example there, the D is literally the distance between the middle of the cation and the middle of the anion. And as that distance gets bigger, then the force gets smaller. And conversely, if the distance between the ions gets smaller, then the force gets bigger. So on the right-hand side in the lower part, you can see there's a small distance and there's also a big distance. And the small distances will have a much stronger force. Things in the bottom are the opposite. So small in the bottom means big in the top. So small distance means big force. And oh man, if those two ions are close to each other, that usually means you have a really strong force. On the other hand, in the bottom there, it's showing you have a big distance between them. Big distance means small force. They're opposite each other. So those are the two things that affect ionic bonds. The more charges you have, the stronger the force will be. On the other hand, as the distance between the ions gets smaller, the force gets bigger as well. So on the left-hand side there, then we can start talking about this. Coulomb's law describes electrostatic forces, the strength between the positive and the negative parts of the ion. As the ion charges increase, your attractive force increases as well. All right? So the charges get bigger, the attractive force gets bigger, and you have a stronger bond. On the other hand, the next one, as the distance increases, then your attractive force begins to decrease. So the distance is opposite. So if you want the strongest bond possible, you want the maximum number of ionic charges. So like +2 or -2, or even better yet, +3, -3 would be even stronger. But you also want them to be as close together as possible. The smallest distance between the ions gives you the biggest ionic charge. This is the gist of Coulomb's law, and that's what chemists usually use. We don't usually calculate anything, but we will use this to talk about the strengths of bonds.
Atoms have three distinct electrostatic interactions with each other. The electrons repel. Similarly, the nuclei repel each other. Finally, the electrons on each atom are attracted to the nucleus of the other atom. When this attractive force is greater than the combined repulsive forces, a chemical bond forms. The energy of two atoms varies with distance, according to the interplay of the attractive and repulsive forces between them.
It's amazing that bonds form at all when you think about it, because wow, I mean, why would the atoms want to come together? It's kind of cool. When it comes to covalent bonds, which is the sharing of electrons, you have to remember that there's both attractive and repulsive forces when those two atoms come together, because you don't have the +1, -1 ionic charge at this point. Everything's being shared. So on the left-hand side there, the little black dots, those are the nuclei of the atoms, and the kind of gray, I don't know what color that is exactly, but anyway, that's the electron cloud around the nucleus. Now, opposites attract. So the positive nucleus on one is attracted to the electron cloud on the other atom, and vice versa. The positive nucleus on the second atom is attracted to the electron cloud on the first atom. But there's also repulsive forces, because electrons don't want to be next to each other, and the nuclei don't want to be next to each other. So it's a combination of these forces that has to be overcome if you're going to make a covalent bond. And what this means is that sometimes covalent bonds just won't form, all right? You're going to have more repulsive forces than attractive forces, and it's just not going to happen. Now, on the right-hand side, that little video right there, it showed that there is going to be some optimum distance where you have the best overlap, the best bond, best covalent bond. And if you're too close, the repulsion gets too high. It's not going to happen. But on the other hand, you get too far away, then the attractive forces can't kick in, and you won't make a bond at all. So there's always going to be some optimum bond length that's going to happen, and every two sets of atoms will have their own optimum bond length. Now, in addition, when it comes to covalent bonds, sometimes you have perfect sharing between two atoms. So, for example, if you have two nitrogen atoms, they're going to share electrons to the same amount. Nitrogen will share its electrons with the second nitrogen to the same extent that the second nitrogen will share with the first nitrogen. And they call those pure covalent bonds, or just covalent bonds. But what happens most of the time is that you'll have two opposite atoms, like maybe a nitrogen and an oxygen, or a nitrogen and a carbon, something like that. And each of those will have its own sharing abilities. You're going to have unequal sharing of the electrons, and they call that polar covalent. So we'll talk a lot about polar things. Polar things are when you have atoms in a molecule that don't share electrons to the same extent. Hydrogen monochloride, HCl, is an example of a polar covalent bond. Chloride, we're going to see, is it pulls electrons a lot more than the hydrogen does. So notice this weird nomenclature. This is a delta. It's a lowercase Greek letter, and you can see there's a delta negative by the Cl and a delta plus by the hydrogen. So this delta symbol says that the chloride is pulling more electrons its way way. It's more like a negative bond. And the H doesn't pull as well, so it has less electrons around it. It's going to be the more positive side of the dipole. So HCl is a polar molecule. It has two dipoles. It has a negative dipole by the chloride, and it has a positive dipole by the hydrogen. And most bonds are this way. They have slightly positive and slightly negative centers, all right? Unless you have something like N2 or O2, or if you have two atoms that are the same in a bond, most of the time you'll end up with these polar covalent bonds where you have dipoles. Now, if you have a dipole moment, that's actually a measurable amount of dipole, and this is a pretty cool kind of thing. A polar molecule, if you have it, will actually align itself in an electric field. So notice in the bottom part right there, there's a positive and a negative. Well, remembering the opposites attract, those triangles there represent molecules, and the white triangle, those are going to be the delta negative, the negative side. They're attracted to the positive sides. On the other hand, the blue triangles, those are the positive dipoles. They're going to be attracted to that negative part on the right-hand side. So polar molecules, you can sometimes separate them from nonpolar molecules by putting them in an electric field. Now, on the right-hand side, it shows what nonpolar molecules do. They could care less about your positive, negative centers because they don't have anything to be attracted to. They just kind of sit there and float and stuff like that. So this is kind of a cool way, and they do this sometimes with DNA and stuff. If you see this little symbol, this is mu. It's a Greek letter. This is actually a measurable amount of dipole. It's usually measured in something called a debye. You don't need to worry about that, but people can measure how polar molecules are, and it's kind of cool. If you're curious how polar an atom can be, it's definitely something that can be figured out, and it's figured out through something called electronegativity. Electronegativity gets the symbol chi, which looks like an X. It's really a Greek letter, but that's okay. If you write an X, it's not a big deal. But anyway, electronegativity is a measure of an ability for an atom to attract electrons to itself. And if you look here, this is the periodic table, and generally speaking, electronegativities get bigger as you get up and to the right on the periodic table. Now, couple of things. Fluoride is the most electronegative of all. Fluoride has a value of electronegativity of 4.0, which is very high. It's the highest one of all of them. And you can see that more or less as you get farther from fluorine, the values begin to go down. So generally speaking, electronegativity gets bigger as you go up and to the right, or it gets smaller as you go left and down. Either way you want to think about it. Notice the noble gases aren't there. Noble gases don't usually react to make compounds, and they're usually exempt from electronegativities. But in advanced circles, sometimes they will assign electronegativities to the noble gases, but that's something we probably won't see. So electronegativity is what we're going to use to talk about most polar and less polar. So as an example, let's say you had a carbon and a fluorine bond, and you were curious which side would have that delta negative. It would be more negative, or delta positive, more positive. Well, the bigger electronegativity would have the negative side, so that's going to be the fluorine. And the delta positive, the one that isn't pulling electrons as much, that would be the carbon, because it has a smaller electronegativity value. And you could compare atoms for everything on there. And some of them have the same electronegativity values like nitrogen and chlorine, but overall the differences are what allow then these polar bonds to be figured out. For Chemistry 221 through Chem 223, if the atoms are different, we're going to assume that they have different electronegativities and they will be polar, even though really we should look at the values to compare. When it comes to electronegativities, fluorine has the maximum value of electronegativity. And again, going farther from fluorine, the values tend to get smaller. And generally, it goes left and down to figure out what kind it is. Now, in some books, they will use differences in electronegativity to find out if you have a pure covalent, polar covalent, and ionic bonds. We're not going to follow this very carefully, but I do want you to know about it if you hear it. And in our book, it says that a pure covalent is if you have electronegativity electronegativity difference of less than 0.4, polar covalent 0.4 to 1.8, and ionic is greater than 1.8. There's controversy about this. We're not going to follow it real careful. What's important in our class is that you'll only have a pure covalent bond if you have identical atoms, so two N's coming together, two F's, two O's, those kind of things. If there's differences in the atoms, like an N and an O or an N and an F, then you can assume it's going to be polar. And if it has a metal in it and a nonmetal, we'll consider that it's going to be an ionic bond. So if you hear these kind of things, this is where they're coming from. It's not a big deal, but it does sometimes help you to understand what people are saying. So here's the kind of question you might see. It says, which of the following groups of elements is arranged correctly in terms of increasing electronegativity? And you kind of need a periodic table for this. Periodic tables will help you see which ones, where the patterns of electronegativity go. And remember that fluorine is the most electronegative, and as you go left and down, you get farther and farther away from fluorine, and the values of electronegativity get down. So if you want to increasing electronegativity, you definitely want to make sure that your fluorine is at the end, because that's the biggest one, all right? And then you want to kind of go left and down from there in order to figure out the patterns of electronegativity. So aluminum is definitely most left and down of that list of 4 elements, all right? So aluminum will be the least electronegative. And then if you go up, you'll get to boron. So right above aluminum on the periodic table is boron, so that would be next. And if you go right, you'll get to oxygen, which is second highest in electronegativity, by the way. And then finally, you'll get to fluorine, which is the king of the electronegativities. So the answer C here would be the right one. That would be the order of increasing electronegativity. And notice how we went up and to the right in order to figure that out on the periodic table. You don't have to have the values of electronegativities in front of you. You can just use the periodic table, and it works pretty well. So here are 2 bonds, an OH bond and an OF bond. And the question is here, which bond is more polar? Now you can also see this as which one has a more dipolar interaction, and dipolar would just mean the biggest difference in electronegativity. So for a question like this, I would refer to an electronegativity value of table or something like that. I would look up oxygen, which is in both, and then compare oxygen to hydrogen and oxygen to fluorine. So if you do that, you see the oxygen has a value of 3.5, and you can look back on that table if you'd like. Hydrogen is 2.1, and fluorine is 4. So what we'll do here to answer this question is we're going to find the difference in electronegativity, delta chi. So 3.5 minus 2.1, that's the difference. That would be 1.4. And the other two, just think of an absolute value. 3.5 minus 4, of course, is minus 0.5, but we just care about absolute value, so let's make it positive 0.5. If you want to call it negative, it's no big deal. Anyway, these numbers are helpful to chemists because an OH bond has a bigger delta chi, a difference of electronegativity, than OF. So that means that OH is more polar. And in this context, what that means is hydrogen's going to be definitely more of a positive side, and oxygen will be more of a negative side. You'll see a positive negative on OH a lot more than you would have on OF, because OF doesn't have as big of a difference of electronegativity. But the other interesting thing about this comparison is oxygen has a bigger electronegativity than hydrogen. So that means that oxygen's going to be negative when it's compared with hydrogen. But with fluorine, fluorine has a higher electronegativity. It's the biggest of all. And notice that the oxygen is actually the positive part when it comes to the OF. So the polarity is, if you will, reversed. Oxygen is negative with hydrogen, but it becomes positive with fluorine. And that shows how versatile these elements can be. And it also shows the value of electronegativity values. So here's a question you might see. Here are 5 different bond types, and it says which of the following will be expected to have the greatest bond polarity. Now in this problem, we don't probably have a table of electronegativities next to us, but if you did, you could absolutely use a table and you could compare. You'd look for the biggest delta chi like we did on the last example. So if you don't have a table of electronegativities, what you want to do is you want to pick the 2 elements which are furthest from each other on the periodic table. So looking at that list then right there, first of all, the very last one, F and F, even though fluorine's most electronegative, that's a fluorine with another fluorine. So delta chi, the difference of electronegativities, would be 0 for that. So that's actually a non-polar bond. There wouldn't be any difference there. And if you look at all those different ones, notice how answer B has a potassium. Now potassium is on the far left of the periodic table, much farther than anything on that list, to the left anyway. And fluorine is definitely far to the right. So the biggest difference between the elements would certainly be K and F. So this would be the way to answer questions like this without it. The atoms that are farthest apart will have the greatest bond polarity. KF isn't just polar, it would be truly ionic because you have a metal and a non-metal. So that would have a true positive and a negative center. No sharing of electrons here. But even from that, we can find that potassium would be the positive part, smaller electronegativity, than fluorine, which has a bigger electronegativity. So all of these rules have led up to what's called a Lewis electron dot structure. And one of the great American chemists, his name was G.N. Lewis. And Lewis created these rules to try and figure out how electrons are distributed around molecules. And it's a very cool set of rules that we'll use a lot. The rules are pretty chill. And once you do that, you'll be able to see how electrons are placed around atoms in molecules. And that can be pretty powerful. And in a nutshell, Lewis had this set of rules to take the outermost electrons, which he called valence electrons. So valence just means outermost electrons. And you can take those outermost electrons and put them around the molecule as bonding pairs when you have lone pairs between 2 different atoms. I'll abbreviate them BP quite a bit. And also you can put electrons as lone pairs. And a lone pair is just a pair of electrons that are on a single atom. They're not being shared with anything else. So let's check out how a Lewis structure works. To figure out how a Lewis structure works, we have to talk a little bit more about valence electrons. So we talked in an earlier chapter about the total number of electrons in an atom, but not all of those electrons will be involved with bonding with other molecules. Some of them are deep inside the molecule. They're too close to the nucleus to make any bonds. However, some of them will be on the outside of the atom, and those are the ones that will make bonds to other atoms. So the valence electrons are the ones that are going to make bonds with other molecules and atoms. On the other hand, we'll talk about core electrons. Core are just too deep inside the atom to make connections with other atoms. So Lewis structures, we need to know how many valence electrons we have before we start building them. For main group elements, which is mostly what we're going to talk about in this section, and by the way, main group elements are the A groups mostly, so 1A and 2A on the far left, as well as 3A through 8A on the right-hand side. The number of valence electrons basically equals the group number. So let's look at some examples here. Carbon is group 4A on the periodic table, but we know from our earlier interactions that carbon has a total of 6 electrons. So this 4A, the 4 is what we're after. 4 means it's going to have 4 valence electrons. And since carbon has a total of 6 electrons, we can talk about the core electrons, which are the electrons that won't be involved with bonding. It's total electrons minus valence electrons. Carbon's going to have 2 core electrons. So 2 of carbon's electrons won't be involved with bonding with atoms at all, but those other 4 are going to be really important, as we'll talk about in a little bit. Bromine is in group 7A, so that means it has 7 valence electrons. Bromine has a total of 35 electrons, so 35 minus 7, bromine has 28 core electrons. Down here it shows actual electron configurations. This is for sodium. Now if you remember, sodium is 1s2, 2s2, 2p6, 3s1. And as the n number, 3, 2, 2, and 1, if you remember, as the n number gets bigger, the electrons get farther and farther from the nucleus. So sodium in group 1A has 1 valence electron. It's going to come from that 3s1 orbital. And that 1s2, 2s2, 2p6, that neon core, those are all core electrons. And honestly, they're boring for chemists. We don't really care about those. So valence electrons are just the outermost electrons. And you can go back to all the electron configurations. It's usually the highest n electrons that are involved in the bonding. So if I said, how many valence and core electrons does boron have? Well, boron is in group 3, 3 valence electrons. Boron has a total of 5 electrons, 5 minus 3, 2 core electrons. And likewise there in the bottom, fluorine has a total of 9 electrons, but it's in group 7A, so 7 valence electrons, 9 minus 7, 2 core electrons. So here's a kind of question you might see. It says, how many valence electrons are in phosphorus? All right, so phosphorus is number 15 on the periodic table, but what we want for this answer is we want to know what group it's in. And this is where it's really important to use the quote-unquote American version of the periodic table, where we have phosphorus in group 5A, not number 15. And that 5A means that it's going to have 5 valence electrons. So that's the advantage of the American quote-unquote periodic table, because the group numbers can literally tell you the valence electrons, and the valence electrons are used to build molecules, so that's why they're so important. This is an example of a Lewis structure for hydrogen monochloride, HCl, all right? And if you look at this structure, there's a line between the hydrogen and the chlorine, and that's called a bonding pair. And a bonding pair represents 2 electrons, so the H and Cl are connected by 2 electrons. It's like a handshake, all right? There's a bond between the H and the Cl. But Cl has a bunch of double dots around it. You can see there's 1, there's 2, and there's 3. And they call those lone pairs. Lone pairs are pairs of electrons, 2 electrons that are just around one atom. So HCl has 1 bonding pair between the H and the Cl, and the Cl has 3 lone pairs around it. And so this is what they call a Lewis structure, a Lewis electron dot structure. Now, bonding pairs should always be lines. Do not use dots for bonding pairs. That's a big no-no when it comes to chemists. On the other hand, lone pairs should always be dots. Don't use lines, all right? So make sure you follow this. This is important to chemists. Bonding pairs are lines. Lone pairs are literally dots. Don't use lines for them. Also notice that around the chlorine, there are 3 lone pairs and 1 bonding pair, for 4 pairs total. And we'll talk about this here in a little bit. But more or less, atoms want to have usually 4 pairs around them. Now, hydrogen does not. Hydrogen is so small, it's happy having just 1 pair. And we'll talk about this here in a little bit. We'll come back to this idea of 4 pairs around a central atom. So if you're going to build a Lewis structure like HCl or H2O or any other combination, generally speaking, the number of bonding pairs around an atom that's in group 1A through 4A will equal the group number. On the other hand, if you have an atom which is 5A through 7A, like chlorine for example, the number of bonding pairs will equal 8 minus the group number. So let's think about that in terms of HCl. Hydrogen is in group 1A. It has 1 pair around it, and that's actually really happy. On the other hand, chlorine is in group 7A. So 8 minus 7, it wants to have 1 bonding pair, and that way makes it pretty happy. And that's a pretty good rule overall. We're going to see there's some exceptions, but if you have to make a guess, that's a pretty good place to start. Except for hydrogen and a couple other things we'll talk about later, generally speaking, bonding pairs plus lone pairs will equal 4. So if you look at chlorine, chlorine has 3 lone pairs and 1 bonding pair. 3 plus 1 equals 4. Now, each of those pairs is 2 electrons, so 4 times 2 is 8. They call this the octet rule, and an octet rule usually results in a stable configuration of that particular atom. It's not always right, okay? We'll talk about that more later, but more often than not, if you can have an octet around your central atom, pretty awesome. However, we're already seeing that hydrogen only has to have 1 pair to make it happy. So it's not, as I said, perfect, but more often than not, it's great. In Chem 104, which is a lower version of chemistry than Chem 221, the octet rule is seen as the golden rule, all right? And almost always it's followed. But in our bigger class here, we'll see more exceptions as we go through. So let's build a Lewis structure for ammonia. Ammonia is NH3, and ammonia is a pretty important chemical in organic chemistry and in regular chemistry. You can buy ammonia like in that bottle in the lower right-hand side from Kroger of all things. It's a great cleaner for household things. A lot of household cleaners have ammonia. But anyway, if you wanted to build a Lewis structure to see what it quote-unquote looks like, you would first start off by counting the valence electrons. So on the periodic table, which I would encourage you to have in front of you as we go through this discussion, nitrogen is group 5, so it has 5 valence electrons. Hydrogen is group 1. So when you're counting the electrons, there are 3 hydrogens, and each of them have 1 valence, and there's 1 nitrogen with 5. So ammonia has a total of 8 valence electrons. And if you divide that number by 2, it tells you that there's a total of 4 pairs of electrons. So we have 4 pairs of valence electrons to place around the NH3, and that's the first step you want to do. Now, the next thing you want to do is you want to figure out what the central atom of the molecule will be. And the punchline, it's never going to be hydrogen. So for NH3, that makes it obviously nitrogen because it can't be hydrogen. So this is kind of silly. Now, in other molecules we'll see that are a little bit more sophisticated, the central atom is always the atom of the lowest affinity for electrons. What that means is it's the lowest electronegativity atom that goes in the middle. But on a practical level, most of the time, the first atom listed in a formula is the atom that goes in the middle. So for example, carbon dioxide, everybody calls it CO2, nobody calls it O2C. And the reason for that is that carbon is the central atom. It's going to be in the middle. And ammonia, you can see here, is NH3, the nitrogen's first, so that's why it goes in the middle. Yes, there are exceptions. Sometimes the first atom listed is not the central atom, but often it is. Just kind of keep that in the back of your mind. But for this example, yes, nitrogen's the central atom, and we have 4 pairs of valence electrons to place around it. So what I would do is start with putting nitrogen in the middle, put the hydrogens on the outside, and then place a bonding pair between each of those outer atoms and the inner atoms. So there's one line right there, there's a second line between N and that H right there, and a third one right there. Now each of those is a pair of electrons, and the first pair like that is called a sigma bond. A sigma bond will have relevance to us later. A sigma bond is like a single bond, but it keeps the outer atoms from floating away from the central atom. Okay, think about it like that. Now, we had 4 pairs total, and we just put 3 pairs down to keep the outer atoms from floating away. So if you have any electrons left over, you first actually start by trying to put them on the outside atoms, but hydrogen only wants 1 pair, so there's nothing to do that. So if we have any left over after that, we'll put any lone pairs on the central atom, and nitrogen likes to have 1 pair of electrons. So at this point now, you can see that nitrogen has 3 bonding pairs and 1 lone pair. It has 4 pairs total. That's an octet. And nitrogen in group 5 wants to have 8 minus 5, 3 bonding pairs. And you can see that it does. It has 3 pairs to hydrogen. This is the Lewis structure for ammonia, NH3. So pat yourself on the back. You just did your first Lewis structure. Woo, I know you're excited. But anyway, it's a pretty chill process. If you follow these rules through, you'll have no problem. You'll be good to go. One rule about this, A lone pair, like the one on nitrogen, is usually a lot bigger than the bonding or shared pairs that go around it. So that lone pair on that nitrogen is going to take up a lot of volume, and it's going to push the other ones a little closer to each other. So shared pairs are smaller and lone pairs are bigger. And the two electrons in the unshared lone pair, they don't really want to be next to each other, so they take up a little bit more space. We'll come back to this idea here in a little bit. But anyway, for right now, you can see making a Lewis structure, it's not too bad as long as you know how many valence electrons there are and you can figure out what the central atom is. So here's the kind of question you might see, and it says, which of the following Lewis structures is or are correct? Okay, and there's a couple different ways to answer this, but for what we know right now, remember that most of the time the atoms want to have, the central atoms want to have an octet around them, and an octet means 4 pairs of electrons, and they can be lone pairs or bonding pairs. So for example, if you look at structure number 3 there with the phosphorus, that phosphorus is pretty happy because the phosphorus has 3 bonding pairs to the 3 hydrogens and a lone pair. So 3 bonding plus 1 lone pair, 3 plus 1, 4 pairs, that's an octet. So that one should be a happy molecule. And happier doesn't mean it's like skipping around in the sunshine. It means that it has a stable configuration of electrons. I should be a little bit more precise and probably not use flowery language, but what can you say? If you look at the one right below it, though, fluorine only has 3 pairs around it. It has 2 lone pairs and 1 bonding pair, but most of these like to have 4. So I don't think that HF would be very stable in this configuration. The same thing for the other 2 on the left-hand side. Like the oxygen right there has 2 bonding pairs, but that's it. And it needs to have 4, all right? So oxygen needs more electron density around it. And this one right here is similar to what we just drew, except that there's no lone pair on the nitrogen. And without that lone pair, that nitrogen has only 3 bonds. That's not an octet either. So I would say that the only one of these which is correct would be structure 3. All right. It has an octet around the phosphorus. The hydrogens have their 1 bond, so they're happy. Everything here would be in a stable electron configuration, but all the other ones are probably a little deficient when it comes to electrons around the central atom. So let's look at another example. This is for the sulfite ion. And sulfites are actually around a lot more than you might think. If you're 21 and over or 19 and over in Canada and you drink wine, and I'm not encouraging you to or anything like that, but anyway, a lot of wines have sulfites. And so in the upper right-hand corner there, that's the label from a wine bottle. Sulfites are often a preservative, and sometimes people are allergic to sulfites, so they have to be careful, et cetera, et cetera. Anyway, let's draw it. Let's see what the sulfite ion looks like. Now, the difference between sulfite and the earlier ammonia example is that sulfite has a charge, and we'll talk about that here in a little bit. To figure out the central atom, it's usually the first atom listed. It's always the lowest electronegativity atom. Oxygen is second only to fluorine, and there's nothing else as big as oxygen except for fluorine, so sulfur will definitely be lower electronegativity. It's going to be the central atom, but again, it's usually the first atom listed, just to be honest. Valence electrons. Both sulfur and oxygen are in group 6, so each of those has 6 electrons, 6 valence electrons. So sulfur has 6, there are 3 oxygens, and each of them have 6 for a total of 18 from the oxygens. But notice here that I added 2 electrons for the negative charge. Negative charges mean you have extra electrons. You want to add negative charges to your total valence electrons. And conversely, if you had a positive charge, you would subtract electrons. It's a little reverse from what you might think, but it's totally doable. So for this molecule, then there's going to be 6 for the sulfur, 18 for the oxygen, and 2 extra electrons from the negative 2 charge. That's a total of 26 valence electrons. And if you divide that by 2, you get 13 pairs of electrons. So the next thing you want to do, you want to connect the outer atoms to the inner atoms. You want to connect the oxygens to the sulfur. You're going to make what's called a sigma bond, which is just a single bond. Each of those lines connecting the outer to the inner sulfur is a bonding pair. So we use 3 pairs to connect them. That means we have 10 pairs of electrons are left. And what we'll do on the next slide is we'll put them on the outer atoms first. That's something that's always important. And if we have any left over, we'll put them on the inner atom. So when you do that, you can see what happens. We had 1, 2, 3 pairs around the first oxygen, and then that oxygen has an octet. 3 lone pairs and 1 bonding pair is an octet. We'll do the same thing for the next oxygen and the same thing for the third oxygen. So by doing the outside atoms first, all of the oxygens then have an octet. But we do have 1 pair left over, and if you have any left over, they go on the central atom. So even sulfur gets a lone pair, and that makes sulfur happy because sulfur has 3 bonding pairs to oxygen and 1 lone pair. That's an octet. So everything here is totally happy. And so this is the Lewis structure for sulfite. Now, sulfites are very important, like I said, especially for wines. And there are a maximum allowable levels of sulfites and stuff that are set up by different government things, which is interesting. And organic grapes wine, they sometimes have added sulfites. I don't know all the details about why they add sulfites to wines. But anyway, it is kind of interesting how they all go around. And again, people that are allergic to these things have to really pay attention to it. I had a friend that would only drink super organic wine in order to keep the sulfite level concentrations down. If you have a Lewis structure with a charge, a lot of times what people will do is they'll put the charges like this in a square bracket, and then in the upper right-hand corner, they'll put the charge, positive or negative. So sulfite has a -2 charge, so that's why there's a 2- up there. So if you see the square brackets, that's the convention to use when you have an ionic compound. Now, notice that this version of the sulfite ion has a double bond. We'll talk later about why it is a little bit better to have a double bond around sulfite. We'll talk about formal charges in a little bit. Just realize the structure on the left, there's nothing wrong with it, but if you want to get the best structure, then yeah, you do get a little bit better structure if you have a double bond. We'll talk about all this when we get to formal charges in a little bit. Carbon dioxide, super important, greenhouse gases, all that jazz. Let's do the Lewis structure. Central atom, going to be the first one, lowest electronegativity, definitely going to be carbon. Now, valence electrons, we're going to start going through this faster. Carbon is 4 valence, oxygen is 6, and there's 2 of them. So 4 plus 6 times 2, that's going to be 16 valence electrons or 8 pairs. So when we make the Lewis structure, first thing we'll do, carbon in the middle, oxygen's on the outside, connect the oxygens to the middle one using sigma bonds. So that's 2 of the 8 pairs we just put down. Next thing we'll do, we'll put lone pairs around the outside atoms first, and if we have any left over, we'll put them on the inside. Well, oxygen likes to have an octet, so each oxygen is going to get 3 lone pairs. That gives it an octet. So both oxygens here have an octet, and they're happy. However, carbon here feels kind of left out because carbon wants to have an octet as well, and carbon only has 2 bonding pairs around it right now. So carbon is not going to be happy with this configuration. So if you come to this kind of situation, there's a way to give more electron density to your central atom. So what a person will do if they see this, if they see carbon without an octet, is we have to give that carbon more electron density. So what chemists will do when you're drawing a Lewis structure is they'll take a lone pair from each oxygen and start sharing it with the central atom. So you can see there on the right-hand side there, carbon dioxide actually ends up with carbon having 2 bonds to the first oxygen and 2 bonds to the second oxygen. Now, oxygen doesn't feel slighted really. It's taking a lone pair that was all by itself and sharing it, but oxygen can still count that pair. So the oxygens have 2 bonding pairs and 2 lone pairs for an octet, and they're happy. And the advantage now is that the carbon has 4 bonding pairs around it. This is its octet, so all the atoms in the molecule will have a more stable configuration with this version of CO2. Now, the second bond that's formed is called a pi bond, or it gets the Greek symbol pi. And this is different from the math pi 3.1416, etc., etc. This is just called a second bond, and it's a pi bond. So in the CO2 structure, the black lines you could think of as sigma bonds, and the red line you can think of as a pi bond. And a sigma plus a pi bond is what a double bond is. We have two double bonds around the carbon in CO2. So this leads us to questions like this that says, which of the following Lewis resonance structures is incorrect for N2O? We'll talk about resonance structures here in a little bit, but what I'm really more interested in you seeing is I want you to see which one of these structures is not a good Lewis structure. Now, if you look at all of them, and I would focus on the central atom, the nitrogen, you want to look for nitrogen to see if it has an octet. So in the first one there, nitrogen is like carbon in CO2. It has double bonds on each side. So that's 4 pairs of electrons around nitrogen, and 4 pairs is kind of the gold standard, if you will, for these things. So that would be a good structure for N2O. If you look at number 2, there's a triple bond, which would be 2 pi bonds and a sigma bond, by the way, but that's 3 pairs of electrons to the nitrogen and a single pair to the oxygen, 4 pairs total. So that nitrogen is actually legit as well. So again, note you can have double or triple bonds, pretty kind of cool. In structure number 3, similar, except that now the triple bond is to the oxygen and a single bond to the nitrogen. Well, that's 4 pairs total around nitrogen, and that's okay. But if you look at structure number 4, that central nitrogen has a problem because that nitrogen has 2 bonds to oxygen and 3 bonds to nitrogen. Now that's 5 bonds total. And a real important thing to follow is that anything in that second period, so carbon, nitrogen, oxygen, fluorine, it can never have more than 4 pairs of electrons. So in structure 4, it has 5 pairs. That would be a disallowed combination of electron pairs around nitrogen. That would not be a good Lewis structure. So notice here that for a lot of these things, you have to keep them at 4 pairs or less. You can't have more than 4 pairs. We'll talk about this more in a little bit. So when it comes to double or triple bonds, there's all kinds of examples out there. And these are just a couple of examples that happen. So carbon dioxide we just showed had a double bond. This crazy thing is called methyl cyanide. It's actually used a lot in making compounds and stuff, but it has a carbon-nitrogen triple bond. That's the cyanide bond, and it's actually pretty strong. In the upper right-hand corner, we have acetylene, also called ethyne. It has a carbon-carbon triple bond. So there's double bonds, triple bonds, all kinds of different bonds are possible. Now, we remember from earlier, as the number of bonds goes up, the length between the two atoms goes down. So a double bond is shorter than a single bond, and a triple bond is shorter than a double bond. So the bonds actually get closer together as the number of bonds go up. And we'll talk about this more later, but it is kind of an interesting thing. You do have more energy when you have a double bond versus a single bond, and a triple bond would have even more energy than a double bond. Some of the atoms on the periodic table can violate the octet rule and get away with it. So in the example I showed earlier, that nitrogen had 5 bonds, that certainly breaks the octet rule, and that's not allowed. So let's talk about when you can break the octet rule and when you can't. So some atoms can go under the octet rule, like they can have only 3 bonds around the central atom, or even sometimes 2. So let's look at boron trifluoride, which is actually a stable molecule. Boron would be the central atom. Boron has 3 valence electrons. Fluorine is 7, and there's 3 of them. So 7 times 3, 21, plus 3 from boron, that would be 24 valence electrons, or 12 pairs of electrons. And when you complete the Lewis structure, boron's in the middle, 3 fluorines around the outside, but notice here in this version, boron has only 3 pairs. And this is definitely a stable configuration for boron. If you have boron, aluminum, gallium, or beryllium, they can actually go under an octet. And boron, aluminum, gallium will be happy a lot of times with just 3 bonds around them. Beryllium can actually get by sometimes with only 2 bonds around it. There aren't too many of these that go under the octet. Most of them want to have at least an octet, but these atoms can go under. Now notice that carbon, nitrogen, oxygen are not on this list. They will never have less than 4 pairs, all right, and that's important. But boron, beryllium, aluminum, gallium, they can go under the octet and be okay. Some atoms are able to go over the octet rule. One example of this is sulfur tetrafluoride. Let's build the Lewis structure. Central atom, sulfur, less electronegative than fluorine. Fluorine's the most electronegative of all. Sulfur has 6 valence electrons, fluorine has 7 valence electrons, and there's 4 of them. So 7 fluorine times 4 fluorines would be 28 valence from just the fluorines, plus 6 for sulfur. That's 34 valence electrons, or 17 pairs. So when you build the Lewis structure, put the sulfur in the middle, fluorines on the outside. Give the outer atoms a filled octet first, and if you have any left over, put it on the central atom. And when you do that, lo and behold, sulfur ends up with an extra lone pair on it. And this is actually a stable configuration for sulfur. In this case, it has 5 pairs of electrons around it. It has 4 bonding pairs, 1 to each of the fluorine, plus a lone pair. And so what's important here is that this is actually very common outside of the second period. So periods go left to right on the periodic table. The second period would be starting with lithium and going over to neon. And if you're outside the second period, like third period, fourth period, etc., sulfur, selenium, tellurium, these kind of things, they can have more than 4 pairs. It's also important to recognize then that the second period will never have more than 4 pairs. So what that means here is, again, carbon, nitrogen, oxygen, these things will always have 4 pairs. They won't go under, they won't go over, they have to have 4 pairs. So we're seeing here that boron, beryllium, aluminum, gallium, they can go under 4 pairs. And if you're in the third period and lower, you can have more than 4 pairs, like the sulfur here. But it's also important that carbon, nitrogen, oxygen, never more than 4 pairs. Atoms in the first and second periods cannot go over the octet rule, and that's a hard rule. I've never seen exceptions to this. On the other hand, third period and greater, you can go over the octet rule. It's not that they have to. Like a lot of sulfur compounds have just an octet around them, which is great. But if they need to, they can go over the octet rule. And we'll see examples of how this works out here, definitely.